Hello everyone. I'm sorry Eric and I can't be with you, but hopefully by sending the presentation you can get some of the ideas that Eric and I have been working on for a while. What we want to talk about is the lessons in estuarine restoration, and a lot of what I talk about is revolving around a global review that we've just done of estuarine restoration methods. In essence, we need to restore sites that have been degraded. As you see from that red dot, that is the pristine site. We do things to it and it degrades. If we don't put any mitigation measures, it degrades the black dot that you see there. So we rehabilitate it, or we restore it, or we remove a stressor and let the area recover on its own. We might even try and compensate the area. If we can't recover it on its own, then we can build new sites. And this is what I want to explain to you right there. We have to think about the trajectories of recovery, the way a system resists change, and then the way that it's resilient to change. It bounces back after some sort of change. So we're interested in these trajectories of recovery. And there's been a lot written about these now. So what do we restore? What do we recreate in all this? Firstly, we have to either restore or recreate the shape and the connectivity, getting the physics right, the hydrodynamics, the ecotones, the supply of water, the connectivity of an estuary with the areas upstream or the areas out at sea. We then have to recreate the surface area and the biogeochemical pathways, the delivery of nutrients, the sequestration of carbon, creating feeding areas. If we can get this right, then we can eventually create the habitat complexity, which allows the ecology to develop and gives us both the structure of the ecology, but also the functioning of the ecology. So for a while now, Eric and I have been thinking about estuarine ecohydrology, the science and our understanding of the links between the physical system, the way if we ensure that the waters and the sediments and the shape are okay, then eventually we can get the right sort of ecology. Now, if we know we've got that estuarine ecohydrology right, we can eventually lead to conditions where the ecology will develop. And developing the ecology is what has become called ecological engineering or eco-engineering. And for a while now, we've been thinking about these two types of eco-engineering. The first type is where you modify the physics of the system. You get the shape right, you get the freshwater flows. We get those right in order to produce the ecological niches in the area. If they're right, then the ecology will follow. And that. The second type, and this is what we call type A eco-engineering. The second type, which we call type B eco-engineering, is where you're engineering the ecology directly, where what you're doing is either restocking, say, fish, or you're replanting reed beds or seagrasses. You're giving the ecology a helping hand. And so both of these types are being used worldwide. If we put these two together, eco-hydrology with eco-engineering, we can try and get the best of all worlds. We can try and get the system to function properly on the physics and the hydrology, and we can get the ecology to come in. So we're trying to recreate ecosystems which at least have some attributes of the original ecosystem. If we can do this properly, we get all the benefits. We get a benefit for the ecology, but we might also get a benefit for society by creating the right sort of ecosystem services provided by a system. We're trying to restore systems to overcome historical loss, to try and restore systems where we're trying to put back wetlands that have been removed over time, that have been lost through building on estuaries. So in essence, the eco-hydrology is the science and the theory behind this, and eco-engineering is the way we put into place mechanisms to try and get that recovery of the ecology. So we can then say, okay, there must be a set of ecological engineering or eco-engineering principles, and these principles are shown here, that we want to ensure a physical chemical system is right. We want to ensure that a particular site works the way it should be. So we need a site-specific solution to this. We want simple solutions because, as we know, if we have very complex solutions, they often don't work. And we want to make sure that the system is linked in the way it should be, that we have the right connectivity between the catchment and the estuary, and between the estuary and the sea. And if we have those, we get the right ecology back, we get the fish back, and we get the birds back, the invertebrates and the plants and so on there. So then we need a set of measures in order to get that ecology functioning as the way it should be. Now, we use the term measures because this has been put into various parts of governance, of legislation. In Europe, we talk about measures to try and improve the seas or measures to improve estuaries. So this shows the types of ecological or eco-hydrological measures that we can have. Firstly, the hydrology and the morphology, measures to change tidal ranges or to stabilize coasts, to stop erosion, or to change the need for dredging in areas, or to zone an area so we have control over what's happening there. So we have a set of these hydrology and morphological measures. We have physical chemical measures, and most of these revolve around stopping putting in pollutants, restricting the way nutrients going into the sea or pollutants are going into the sea. So these are measures that we can bring in, and measures that may be defined in law. And then next we have the biological, the ecological measures to protect habitats, or measures to ensure that specific species are occurring there, measures to ensure we've got connectivity. And then finally, we've got measures for human safety, to ensure that areas are not getting flooded, that livelihoods are not at risk, that erosion is not creating problems for habitats and so on, to increase the resilience of systems. And of course, this is quite important now with sea level rise and other coastal hazards. As a quick example of this is a habitat restoration scheme that was designed to try and improve a system and replace an area that was going to be lost because of port development. As you see here, this is the area, it's being prepared, it's the right levels being created, the right conditions for sediment to come in are being created, again to replace habitat that was lost because of a port development. This is a year later, and you see there that the aim was to create a mudflat, and a mudflat has been created there. It seems to be functioning properly. It's got shell duck feeding on the invertebrates in the mud. It seems to have the right sort of creeks. It looks like a mudflat that was lost by port development. So it seems to have the right structure, and as far as we can see from that, it has the right functioning as well. But look at it 9 years later. The area was silted up. The dynamics weren't correct. There was too much silt coming in. That settled out. It raised the level of the land there. And as you see there, it's not a functioning mudflat, which was the original aim. So it's not worked in a way to compensate for a loss of area. Another example is the peel harvest system in Western Australia. As you see from the map there, it's a very enclosed estuarine area. It has a very small channel, there's a lot of nutrients going into the system, and this made it eutrophic. So in the early 1990s, they created a new channel there, the Dawesville Channel, as you see there, and the Dawesville Channel was aiming to open up the system and increase the flushing there. And it succeeded. It reduced some of the eutrophication system, but not all of it there. So ecological engineering, it'll never create the pristine systems that we had before, but it might have some of the original attributes of those systems. It needs to be accompanied by land management, by the management of pollutants and so on, but it needs to be a holistic system. You need to be able to control all of these aspects, especially given that we're trying to reverse problems that may have occurred over hundreds of years. The aim is to try and get the right sort of technologies, and especially if we can get those technologies to make a system that is resilient to natural change and resilient to human change, such as climate change, then it will work. The picture you see there is Richards Bay in South Africa, where the aim was to try and open up a system and give connectivity by creating a channel there. But in the end, the engineering didn't work. The channel just didn't work. So we need a system where we have all aspects covered. And for a while now, we've been writing about the 10 tenets. And these are the features that you need in order to get sustainable management. For example, you need your management to be ecologically sustainable. You need to create the right sort of ecology. But you need the right equipment, you need the right technologies in order to do this. You need to be able to build the right channels or build the right areas and that. But we live in the real world. The solutions have to be economically viable. We don't have unlimited money, so we need the money to pay for any development. We need to ensure that the management measures are what society wants, or at least what they tolerate in an area. And we need to work within the law. Does the law allow us to restore systems and recreate systems? And if the law is there, are there administrative bodies, ministries and EPAs, environmental protection agencies, that can do this for us? And is it politically expedient? Are we restoring systems that is in line with what the politicians want us to do there? Is it ethically defensible? Is it ethically right that we should manipulate the environment? And of course, is it ethically right that we should pay for manipulating the environment in some cases where we are paying money now, but that money has to be paid back by future generations? And what about the cultural aspects? If we restore systems, are we in danger of affecting any of the cultural aspects in an area, indigenous tribal land and so on? And then finally, we have to tell people about this. We have to communicate this. So the final main messages in this. We've got good examples worldwide of both good and bad practice, and what we're doing is we're learning from these. We need a long-term vision when we're creating or recreating systems and that. We need to have good objectives. If we don't have a good objective for restoration, we don't know when we'll have reached that objective. Sometimes we try and recreate systems and it really is just good for the ecologist. It's not doing much for the ecology, but it makes society think that we're doing something. There's an adage that once you start managing a system, you have to keep managing it, because otherwise, if you stop managing it, it reverts to something that you don't really want. And as you've seen with all the Estuarine work, the essence is connectivity. If we have connectivity between the systems, between the land and the water, between the fresh water and the estuary, between the estuary and the sea, then we can try and recreate the systems. And then also the measures have to be holistic. They have to take in land, catchment, marine measures, and the estuarine measures. So the main message in all this, if we get the hydrology right, then the ecology follows. If we don't understand the hydrology, then we don't have a chance of getting a sustainable ecology. And that's why one of the main messages that Eric and I have been sort of speaking about for a long time now is to try and get the right sort of eco-hydrology, but also we can use that to get the right sort of eco-engineering. I think that's the main messages. If you need any more information, then there is our email addresses there, so get in touch with us. Okay, thanks for listening.